Hello, everyone. This is Professor Monty. Today we're going into Chapter 7. Chapter 7 only has 3 sections, so we're going to do all 3 sections today, 7.1 through 7.3. Starting with, of course, 7.1, it's called sampling error and the need for sampling distributions. Now, I've already got the definition of sampling error there for us. Sampling error is the error resulting from using a sample to estimate a population characteristic. So, for instance, suppose that I want to estimate the mean. Well, the way I'm going to estimate the population mean is the sample mean x bar. So x bar, let's give it a value of, say, 10. And let's suppose, unknown to us, the population mean is 8. So what we're trying to do here is use x bar to estimate mu. Well, if that's what I'm doing, then the sampling error is just the difference in those two values. So the sampling error in this case is going to be 10 minus 8, or I have an error of 2. So that's how far off my sample number was from what my population number actually was. So is that close enough? Well, maybe so, maybe not. It just depends on how accurate we need to be. But let's build from there. So there's something called the sampling distribution of the sample mean. Let's write that down. The sampling distribution of the sample mean. And what this represents, it's the distribution of sample means. So x bar, sample means, for all samples of size n. In the population. And I know that probably sounds pretty confusing, so let me show you an example of what we're talking about. So let's come up with a sample. This is going to be a really simple sample, but here's my sample. We'll call this an example. So my sample is just going to be the numbers 1 through 5. So we'll call these my x values, but it's just going to be the numbers 1, 2, 3, 4, and 5. And so now, of course, I can graph those. I can plot those on a number line. So say we've got 1, 2, 3, 4, 5. I would just have a dot above each one of them. That's essentially a dot plot of my data. Okay, so say I have that. And let's have that be x. So those are my x values. And it could be a sample. It could be a population. We're actually considering this a population. So I'm going to change that from sample. We'll say this is the entire population. It could be. It doesn't matter. But what I'm going to do from that group, which we're calling the population now, what I of size 2. All right, so now when I do this, these are going to be my samples. So what I'm going to do is I'm going to say the sample, we'll do a list here, and then what I'm going to do is I'm going to find the sample mean of each of my samples, x bar. So let's do a chart here. And so I'm doing samples of size 2. Well, so one sample could be 1 and 2, another could be 1 and 3, 1 and 4, 1 and 5. Or maybe I don't have 1 in there, maybe I have 2 and 3, 2 and 4, or 2 and 5. Or maybe I have 3 and 4, or 3 and 5, and then the last sample would just be 4 and 5. So those are all the possible samples. There's 10 of them. I've got 10 possible samples of size 2. what I'm going to do is I'm going to find the mean. So for instance, in the first one, I just add them up and divide by 2. So I get 3 divided by 2, which is 1.5. And I'll do that for all of these. So 1.5, this is going to be 2, 2.5, 1 and 5 is 6, half of that is 3, 2.5, 3, 3.5, 3.5, 4, and 4.5. So those are all 10 of my possible sample means. But watch what happens when I graph these. So let's graph these right below the other one. So we'll put this over here. And again, we'll go 1, 2, 3, 4, 5. Try to keep it so it matches. But now when I put these in, I have 1.5. So between 1 and 2, I have a 2. I have a 2.5. I have a 3. I have another 2.5. So we'll stack that up in my dot plot. I have another 3. I have a couple 3.5s. I have a 4 and I have a 4.5. And notice what happens here is my graph is a little less spread out than I was before. And remember, if you talk about how spread out something is, what that's talking about, the spread is related to the standard deviation. So that bottom graph has a smaller standard deviation. And it's a little bit more bunched up. So we can see that, which has to do with the spread, but I've got a lot of repeated values here. All right, let's see what we can do with this. So what I'm going to do is I'm going to go into StatCrunch and we're going to do a little number crunching there. So let's do this. I'm going to pull up StatCrunch. Let's see, it's in here. All right, let me pull up StatLab real quick since that's not up. That's unfortunate, but not a big deal. Okay. So we'll go into the statistics slash. Remember, StatCrunch right over here. We can just open that up. Hopefully it'll open up. Sometimes it won't open up like this, and we have to go and we have to, I'm going to regenerate, see if that opens it up for us. If not, we may have to go into a problem and pull it up that way. Let's just click on the StatCrunch website, see if it comes up this way. And open StatCrunch. So let's see, there it is. So we got it. Sometimes we have to go through a couple things to do that. And what I'm going to do is I'm going to list all the values that we had before. I'm just going to list them right here. So remember, we had the numbers 1 through 5. So I'm going to go 1, oops, let's go back up there. I'm going to have 1, 2, 1, 2, 3. For some reason, my enter's not working. 2, 3, 4, and 5. So there's my data. Now what I'm going to do up here for variable 1, I'm going to say that was when n was equal to 1. And then I'll go over here and we'll say, oh, when n, my sample size was equal to 2, and we'll do something here. So let's see, the numbers I had there, 1.5, 2, 2.5, 3, 2.5, 3, 3.5, 3.5, 4, and 4.5. So I had those 10. And now what I'm going to do is I'm going to do a little number crunching here, because remember, it looked like the standard deviation was smaller because I had a smaller spread. Well, let's specifically see. So what I'm going to do is I'm going to go in here and I'm going to go stat. We're going to do summary statistics by column. And I'm going to pick n equals 1, so my first column. And all I want is the mean and the standard deviation. So I'm going to come over here, I'm going to click on mean, I'm going to hold down control, click on standard deviation. So I just get those two, and I'm going to compute it. And it tells us, hey, my mean was 3, and my standard deviation to 2 decimal place about 1.58. Okay, that's interesting. Well, let's look and see what happened when I did a sampling distribution. So what I'm going to do here is let's look at the mean and the standard deviation here as well. So back into stat, summary statistics, columns. This time I'm going to do N2, and I'm going to do the same thing. I'm just going to use the mean and then standard deviation. If I compute that, what I find out, oh, look now what happens. I have the exact same mean, but my standard deviation is smaller. So the standard deviation gets smaller when you're taking samples of a larger sample size. Okay, so we're going to use that idea and talk about specifically what's happening. So here's what's happening. I've got all my values, and we can go back into the notes. So let's go back into the notes. But what we found was this. When n was equal to 1, just our population, we got a mean of 3, and we had a standard deviation of, see if I remember what that was, about 1.58 rounded off. When I have a sample of size 2, so now this is a sampling distribution, the mean was exactly the same, but the standard deviation was smaller. It was about 0.91. Now, they use a slightly different notation here because the mean and the standard deviation was for the population. Well, over here, when n equals 2, that's the mean not of the initial population, but of all the x bars. So we call it mu sub x bar, and similar, sigma sub x bar. So now I've got those two values going for us, and I could do the same with n equals 3, n equals 4, all the way up to n equals 5, since that's as large as my population was. All right, but let me show you something else that's kind of interesting. If I look and I want to find the probability, let's say this, find probability a random selection is within 1 of the true mean. And that was mu equals 3. All right, so let's see. So remember, in our initial population for n equals 1, I'll just put it down in this line here under n equals 1. What we're going to find is the chance that x is within 1 is we can calculate that just using our f over n rule. And what we're going to find, well, remember, the mean was 3. So up here in our list, the mean was 3. Well, within 1 could only be 2, 3, or 4. So 3 of the 5 numbers were within 1 of the true mean of 3. So we had 3 out of 5, which was 0.6. So our probability is 0.6, or we have a 60% chance. Well, with n equals 2, now we can look over in that list that I have off to the side. If I do f over n there, let's get the blue pen out and mark the ones that are within 1. So anything between 2 and 4, that would be within 1 of the population mean of 3. Well, that one's not, but this one is, 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 and 4.5 is not. So this time, 8 out of 10 of the numbers that we could select are within 1 of the population mean. So I've improved my chances that if I randomly select one of these values, or in this case, one of these sample means, I've got an 80% chance that I'm within 1 of the population mean. So I've got a better chance of being closer to the population mean when I take a bigger sample. Obviously, that makes some sort of intuitive sense because the bigger the sample, the closer I am to the actual population size. And once I get all the way to the population size, there's only one mean there, and it is the population mean. So I'd have a sampling error of 0 because there is no error there. Okay, so that's the idea there. That's the big gist of section 7.1. So let's go over and we'll jump into 7.2. 7.2, notice the mean and standard deviation of the sample mean. So here's what we're doing here. From that previous problem, we'll say from section 7.1, what we noticed was what the mean of x bar So the population mean of all those sample means was exactly the same as the population mean. Remember, we got 3 for both of those. What we find out now, the standard deviation of X bar, when the population size is large enough in relation to the sample size, or when we take all the possible samples of size n with replacement, we did it without replacement, what we get is we get a formula that says sigma sub x bar is sigma, but remember, it gets smaller when the sample size increases. Well, I would divide by the square root of n. So the bigger n is, the more we reduce that size, and you get a smaller standard deviation. So the population mean stays the same, but you have less spread. What does that mean? That means when you arbitrarily pick a sample of a bigger sample size, you're guaranteed to have a higher probability of being closer to the actual population mean. So that's what's happening here. There's smaller spread, so the means are going to get closer and closer to the actual population mean, and so we have a higher probability of picking a sample whose mean is close to the population mean. So that's the idea there. Let me show you a problem. Let's post one in here. Let's see if I have it handy. 747. So this is straight out of the book. It says baby weight. The paper Are Babies Normal by T. Clemens and M. Pagano focused on birth weights of babies. According to the article, the mean birth weight is 3,369 grams, or 7 pounds, 6.5 ounces, with a standard deviation of 581 grams. Okay, first identify the population and the variable. Well, the population here is just all babies. So population, all babies. Because what does the problem say? Focused on the birth weight of babies. Any certain babies? No, it just says on the birth weight of babies. So the population is all babies. What is the variable? Well, what were they measuring? Birth weight. So it's the birth weight of babies. Okay, so that's stuff that we learned way back in maybe chapter 1. We talked about variables in an earlier chapter. We know that for sure. Okay, now B is where it starts to get serious. That's this section. For samples of size 200, so n equals 200, find the mean and the standard deviation of all possible sample mean weights. Well, what do we know? We know the mean of all those samples of size 200 is going to be the population mean. Well, they told us the population mean was 3,369 grams. So we're guaranteed that the mean of all the samples of size 200 is also going to be exactly 3,369 grams. That's not going to change, which is good, because if we're trying to use a sample mean to predict the population mean, we want those sample means to have the same mean as the population mean. But the standard deviation of all those x bars is the standard deviation divided by the square root of n. So in this case, it's the standard deviation. They told us 581, that was up here, divided by the square root of n, that was the sample size 200. And so now what happens, I'll just plug this into my calculator, 581 divided by the square root of 200, and I get, we'll go to 1 decimal place, 41.1. And 581. But in this case, the standard deviation of all these sample means, well, it disappeared. The standard deviation of all these sample means comes out to be 41.1, a much smaller spread, so I'm more likely to get a sample mean close to the population mean. And then C says repeat this for samples of size 400. Well, if n equals 400, then mu sub x bar still is equal to mu, so the population mean is still going to be 3,369 grams. But the standard deviation of x bar, standard deviation square root of n now becomes 581, but divided by the square root of n is the square root of 400. And so now if I do this, 581 divided by the square root of 400 is 29.05 or 29.1 if we round off. And so again, we've got a smaller standard deviation, a smaller spread, so we're most likely going to have a smaller sampling error. Remember, the sampling error would be the difference between my X bar and my sigma. So the sample mean and the population mean. So that's what's happening here. We're going to see a nice picture of this in the next section, which we will go to now. All right, so let's go to 7.3. Notice I've already put a picture up here. We start off with this thing called the central limit theorem. And the central limit theorem says for a relatively large sample size, the variable X bar is approximately normally distributed, regardless of the distribution of the variable under consideration. The approximation becomes better with increasing sample size. What in the world does that mean? Well, we have a picture. That figure 7.6 is a picture of this. So let's look at the picture and see what's going on. So in this first column here, what they're doing is they give us the distribution and they say, okay, the distribution of the variable is already normally distributed. But if I do a sampling distribution of all samples of size 2, it's still normally distributed, but the peak's a little bit higher because it's less spread out. Remember, the area under the curve has to be 1, so if it's less spread out, it has to be taller. But what I've done is I've shrunken the standard deviation, so it's less spread out. But notice the peak is still in the same spot. The mean is still the same. If I go down here to samples of size 10, I still have the mean in the same spot, but it's even less spread out. I'm shrinking down the standard deviation. And then samples of size 30 down at the bottom, same thing. Smaller standard deviation, less spread, same mean. So now if I pick something even way out on the outskirts like this, that X bar is going to be very close to mu. Mu's right here in the middle. And so any of those X bars I pick are going to be closer and closer. Before I might have picked an X bar way out here on the second one, and it's pretty far away. There's quite a bit of sampling error here. Here, there's almost no chance for much sampling error at all. So that's the idea there when we're talking about the sampling distribution. Mu doesn't change. Mu sub X bar is the same as mu. Sigma sub X bar gets smaller when n gets bigger. But that's not the power of this. The big power of this is what we see next. So now let's go into this middle column. Now we've got what we would consider a right skewed graph. It's technically, since it's high to low going that way, we could call that reverse J-shaped, but we know it as a right skewed graph. Now, if I take sampling distribution sample of size 2, now I've got this graph right here. And clearly a right skewed graph, hasn't changed the mean, but notice when I get to samples of size 10, it's looking pretty much like a normally distributed graph. It's still, the peaks is still a little bit to the left, so it's still a little bit right skewed, but not much, and that's only with samples of size 10. Go down to the bottom one, the mean is in the same spot as the population mean. And that graph looks almost identical to the graph we have here. So when I get up to n equals 30, samples of size 30, the distribution, even of this right skewed graph, essentially looks identical to the distribution of a normally distributed graph. What does that mean? That means I can treat it the same way as a normally distributed graph. So if I'm trying to find a z value, if I'm trying to find a probability using the z curve or the standard normal curve, I can do it even though this wasn't a normally distributed population, if the sample size is at least 30. And then the last one, the last column we have over here, notice the same thing. I start off what's called a uniform distribution, samples of size 2, now it's kind of a pyramid or triangular distribution, but at samples of size 10, it looks pretty much like a normal distribution. And at 30, pretty much all these look the same no matter what the underlying distribution was. So what the central limit theorem is saying, notice up here it says for a relatively large sample size. Well, we're going to take that to be down here, a relatively large sample size, we're going to consider that to be 30. So we can say this, if n equals 30, the sampling distribution is normally distributed. Regardless. Uh-oh, that didn't look good. Where's my undo button? Regardless of the, we'll say the population's distribution. I'm going to erase this all while I'm here too. And obviously, if we can do it for 30, we can do it for 31 or 40 or 90 or 100 or 200 or whatever. So let's change this equal to greater than or equal to. So as long as the sample size is at least 30, the sampling distribution is normally distributed regardless of the population's distribution. And we'll say we can then find normal probabilities, or run tests that require normal distributions. Oops, forgot normal. That's why we care. Okay, so that's the big one. If n's greater than or equal 30, the sampling distribution is normally distributed regardless of the population's distribution. That's what we want to get out of this section. Okay, so let me show you a couple things. I'm going to do another quick post right here from something from the notes. It's essentially what we just said, but let's say it a little bit cleaner. So it's when they talk about the sampling distribution. So let me copy and paste this in for you so you can see it. And we'll just go through this to highlight what I'm trying to say. Sampling distribution of the sampling mean. Suppose that variable x of a population has mean mu and standard deviation of sigma. Then for samples of size n, the mean of x equals the population mean, or mu sub x bar equals mu. The standard deviation of x bar equals the population standard deviation divided by the square root of the sample size. Sigma sub x bar equals sigma over the square root of n. Those are the two formulas we saw. If x is normally distributed, so is x bar, regardless of the sample size. What does that mean? Well, over here I had a normally distributed population. Well, as the sample size increased, it's still a normally distributed population. So that's what they're saying. It doesn't matter the sample size, regardless of the sample size. The population is going to be normally distributed if the initial population was. But this last one is the key that I just said. If the sample size is large, x bar is approximately normally distributed regardless of the distribution of x. What does that mean? Well, that means these other ones. If I'm not normally distributed for my population, but I have a large enough sample size, then it is considered to be normally distributed. Not the population, but the population of samples of size 30 or more. So then I can use those nice properties. All right, let's apply this to a problem to see how this all works. Let me go grab a problem. And it's 771. As you can see, there's a little bit of verbiage here. So we'll read through that fairly quickly. All right, 771, nurses and hospital stays. In the article, a multifactorial intervention program reduces the duration of delirium, length of hospitalization, and mortality in delirious patients. There's a long title for you. M. Lundstrom et al. Investigated whether education programs for nurses improve the outcomes for their older patients. The standard deviation of the length of hospital stay on the intervention ward is 8.3 days. For the variable length of hospital stay, so there's my variable, determine the sampling distribution of the sample mean for samples of 80 patients. Okay, here's what we noticed. There's 80 patients, n equals 80. This is part A. Since n equals 80, what do we know? Well, the sampling distribution of all samples of size 80, since that's 40 or larger, since that's 30 or larger, is normally distributed. So we know that sampling distribution is normally distributed. What else do we know? We know that mu sub x bar is equal to mu, which they said in this case, did they tell us what the mean was? I don't see the mean. But we know mu sub x bar equals mu. What else do we know? We know sigma sub x bar is sigma divided by the square root of n. Well, in this case, they said the standard deviation was 8.3 days. N we know is 80, so it's divided by the square root of 80. Well, let's do this. We'll do this. I'm going to go out to 3 decimal places because I'm going to do some calculations. So 8.3 divided by the square root of 80. So I know my standard deviation is about 0.928. So that's rounded off to 3 decimal places. That's what part A is talking about. What does this distribution look like? Oh, it's normally distributed. The mean is mu, and the standard deviation is about 0.928. Now, they tell us in B, hey, wait a second, the distribution of the length of hospital stay is right skewed. Does this invalidate your results in part A? We would say no, because remember the central limit theorem says it doesn't matter what the distribution of the original population is. As long as our sample size is large enough, which in this case is 30 or larger, then it's still normally distributed. So we'd say no, since n equals 80, which is larger than or equal to 30, so we're okay. And then C says obtain the probability that the sampling error made in estimating the population mean length of stay on the intervention ward by the mean length of stay of a sample of 80 patients will be at most 2 days. We're going to use StatCrunch to do this. So what they're saying is calculate probability that when I use n equals 80, that x bar will be, so my sample mean will be within 2 of mu, my population mean. So in other words, sampling error is less than or equal to 2. That's what they're saying. Well, here's what we're going to do. Remember that 0.29 number. Oh, I said 0.928. So that's my standard deviation. Here's what we're going to do. And the sample size, of course, was 80. I'm going to have StatCrunch figure this out. How do I get a probability to be within 2 of the mean? I don't even know what the mean is. That's okay. Watch what we do. We're going to go back to StatCrunch. And here's what I'm going to do. Let's just go to a new variable. Here I'm going to say n equals 80, since we had that in our problem. N equals 80. Now, what I'm going to, I don't even need a column for that. I don't know why I put that there. What I'm going to do, let me close these down so we get these out of our way. And notice they just go saved right over here. We could pull those up if we wanted to. But what I'm going to do, I'm not doing a stat summary. I'm doing stat calculators. And I'm going to go to the normal distribution. Why normal? Central limit theorem. What did it tell us? Central limit theorem says, hey, if your sample size is at least 30, I can assume that the distribution of the sampling means is normally distributed. So that's how I'm going to find the probabilities. Now, we have a problem. They didn't tell us what the mean was. I'm going to leave it at 0, and I'll show you why. The mean can be whatever we want to, but we're going to say 0. Standard deviation, we have that, 0.928. Now, I'm going to say between. 0 is easy to use because they said we want the sampling error to be within 2. Well, if I was centered at 0, that means I'm going to go between -2 and +2. Now when I compute it, that's the probability, 0.69885. We'll call it 0.969. So let me write that down someplace so that we have it. 0.969. Here, let's write out what we see. 0.9688566. And I'll show you why I'm going to do that. We didn't know the mean was 0, and somebody may say, yeah, but the mean's not 0. That can't be the average hospital stay. Okay, well, just make it up. It doesn't matter what it is. We just need to be within 2 days. So say the average hospital stay was 5 days. Now we have to do a little math in our head. So what we're going to do over here is this is going to be 5 minus 2, which is 3. This one's going to be 5 plus 2, which is 7. Because think about it, if we're within 2 of 5, where are we? Well, we have to be somewhere between 3 and 7. That's within 2 of the mean of 5. But watch what happens when I hit compute. I get the exact same 0.9688566. It didn't matter what the mean was, it just mattered what the spread was. All that happened in my picture, the exact same picture up here, the only difference was X. I had 0 in the middle before, and I had -1, -2. And I had +1, +2. So we can put whatever we want in for the mean. They just said if the sampling error was 2, I subtract 2 to get the left side, I add 2 to get the right side. But that's how I find my probability. So that's where I would go and I'd say, oh, it's about 0.969 if I round off to 3 decimal places. So here, and I've already got that there, 969, let's just clear that part of it. So now I'm going to say, oh, it's about, I don't need that. So for part C, it's I forgot what the value was. Good heavens. Was it 969 or 6? Oh boy. That's what happens when you lose your mind. What do we have? And I just erased it. 969. All right. So I'll say, see, I was writing that correctly the whole time. 0.969. There's my probability. But we find that using StatCrunch, just using our probability of a normally distributed population. They even told us, hey, this is right skewed. So typically before the central limit theorem, I couldn't do this problem. I could not find what the probability was. Because think, if it's right skewed, it looks something like this. I don't know how to find these probabilities. If I go, you know, wherever I am, if I go, say this is my mean, and so I'm within here, I'm within 2, well, I don't know how to find that area. That's not the normal curve. It's right skewed. Oh, it doesn't matter. Central limit theorem says as long as my sample size is large enough, what does that mean? 30 or bigger. Then I can assume that the distribution of all the samples of size 80 in this case are normally distributed. And so I can find probabilities using the normal distribution. Okay, so that's the power of this. In this problem, notice we use the normal distribution to find probabilities of something that originally wasn't normally distributed. All right, so that takes us to the end of chapter 7. We're going to use those ideas from here on out. Anytime something needs to be normally distributed, one of two things. Either initially the population's normally distributed. If it is, then it doesn't matter the sample size. But if it's not normally distributed, or if we don't know if it's normally distributed, all we have to do is take a sample of at least 30, and then we're okay. Then we can assume that the distribution of the sampling distribution is normally distributed, and then we can find probabilities. All right, so we're good. That's the end of this chapter, and next time we'll just go into chapter 8.